This is Physics 2212 Lab 5 going over Faraday's Law. Now in this lab we will be observing a magnet falling through a roll of aluminum foil, and we will be actually modeling the same situation through GlowScript and comparing the results of real life and the computational model, and we'll be using this situation to understand Faraday's Law. Now a preview of the results, we get the modeled time for the fall computationally to be 1.579 seconds. Meanwhile the actual fall was recorded to be at 1.45 seconds. Now, principles we need to understand before we get on with the lab: magnetic flux, Faraday's law, the Biot-Savart law, and then Newton's second and third law. Now, the procedure for the lab: first we need to identify north on the magnet that we used using an app on our phones, and then after we got that, we just pretty much need to drop the magnet through a roll of aluminum foil and record the time taken to travel through the roll using video footage. And we need to repeat this 5 times to get an average measurement of time. Now, observations, some more, just pretty much measurements taken from the roll and the magnet. We get a roll length of 29 centimeters. The inner radius of the roll is 2 centimeters. The mass of the magnet is going to be 0.023 kilograms, and then the magnet's magnetic dipole is 2.81. Now, sources of error in this lab ultimately come down to inaccuracies in the measurements, so the roll length, inner radius of the roll, stuff like that, but mainly the magnetic dipole. That's going to affect pretty much everything in the lab later on in the model. Now this is a video of it actually falling through the roll, and as you can see, it looks like it almost slows down, like, when it actually goes through the actual roll of foil. Now moving on to the computational model, starting off with some physical constants. The main one that we add as opposed to previous labs is resistivity of aluminum in ohm meters, so we get 2.65 times 10 to the negative 8th for that. And then moving on to the actual main part of the code, first we need to set up the geometry of the tube. So we do this using the measurements we gathered earlier. But one thing to note is that for the numerical parameters portion, we actually need to divide the length of the roll up into in segments, and we use the in length variable to essentially divide up the roll. And then we go on to actually do pretty much the same for the bar magnet in terms of setting up in the model. Now, initial conditions, we set the bar's velocity, or the bar magnet's velocity, sorry, to be 0 because it starts from rest, and then times equal to 0 at the beginning. And then we use a function to calculate the dipole due to the magnetic field due to the dipole of the bar magnet. And moving on from that, we can calculate the magnetic flux. Now here on the right is getting the net force. So pretty much we start by getting the gravitational force on the magnet. So pretty much that's just negative mass times gravitational constant 9.81. And then moving on, we can calculate the change in flux over time for the ring due to the falling magnet. And then from that, we can actually calculate the magnetic force thanks to that. And then getting the net force is just as simple as combining the gravitational force and the magnetic force together. And then we can use this net force, if you remember back to Physics 1, we can pretty much apply Newton's second law here to using our velocity and position update formulas. Now this is the graph we get from those results and plugging into GlowScript. Now the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Now this can't be seen in this video, but you can check the description and run the code for that GlowScript to see this. But pretty much which color corresponds to clockwise and which is counterclockwise. Blue is going to be clockwise and red is going to be counterclockwise, and we know this just from Lenz's law. Now what happens to the dynamics of the system when you flip the magnet? I tried this and there is no visual change, but one thing to note is that the directions of current will actually swap. We just can't see any actual change. Now, how's the total time in the tube of the real-world system compared to the computational one? It's pretty accurate, both being around 1.5 seconds. One way to actually increase the accuracy of the computational system is just increasing the tube segments, that in-length variable I mentioned earlier. And then also we can, just for everything, just gather more accurate like initialization data, so the dipole for the magnet, the mass, the length, stuff like that. And then how's the shape of the velocity versus time plot tell you about, or I'm sorry, what does the shape tell you about the forces acting? And pretty much you can tell when the forces balance out, so when there is or is not a net force. So as you might remember, if there is a net force, there's going to be a change in velocity, but if there is not net force, there's going to be constant velocity. So as you can see here, the forces are unbalanced So there is a net force. So outside of the aluminum foil, and then there is a constant velocity, so the forces are balancing, and then when it exits, there is a net force again. Now, the resistivity of the conductor, what if what if the resistivity of the conductor were reduced as close as possible to zero? How the dynamics of the falling magnet change? Pretty much greater current, there's going to be greater magnetic force due to Ohm's law. And then what if you put holes or slots in the tube? How this affect the ring currents in your model? And pretty much because there's interruptions, there's going to be less current, which means there's going to be a faster drop through the tube because there's going to be less of a magnetic force counteracting the gravitational force that wants to pull it down. Thank you.